All right. So we're heading towards the final stretch of the chapter. Let's go ahead and finish up. The statement is, an infinite wire runs along the z-axis. It carries a current Iz that is a function of z, but not of t, and a charge density lambda t that is a function of t, but not z. All right, so already based on this statement, we're going to have a fun time with this. By examining the charge flowing into a segment dz in a time dt, show that d lambda dt is equal to negative di dz. If we stipulate that lambda of 0 at time equals 0 is equal to 0, and I at z equals 0 is equal to 0, show that lambda t is equal to kt. I of z is equal to negative kz, where k is a constant. All right, so part B, assume for a moment that the process is quasi-static, so that the fields are given by equations 2.9 and 5.83, or 5.38, excuse me. Show that these are in fact the exact fields by confirming all four of Maxwell's equations are satisfied. All right, let's go ahead and dive in. The charge flowing into dz in time dt is, well, dq is equal to Iz dt, okay, current times time, minus the change in the current with respect to dz times dt, okay? So this is gross and a lot to deal with. Again, with the stipulations there that we had with the zeros, we can kind of consolidate this. So what we have is di dt times dz dt, okay? Minus that, of course, if we were to expand it. But now for dq, we have lambda t plus dt dz minus lambda dt. And in similar fashions, we can expand and kind of contrast this to d lambda dt, and then we have dt dz. It's really weird to see this, but it kind of makes sense because we have, lambda plus lambda over t or dt. It's a lot to deal with, but you kind of have to deal with the whole thing as it comes together. You see these kind of differential relationships in a lot of spaces, so it's worth investigating a little further. But clearly, both of these are dq, so we set them equal to one another, and we see that dz dt and dt dz cancel, and they are related by a negative sign. So indeed, d lambda over dt is equal to negative di dz. Slight typo here. That should be di over dz above for dq as well. All right, but nonetheless, the left side is a function of only t, and the right side is a function of only z, and so they must be constant if their derivatives are equal. So the constant here is k. We solve that. We get lambda t is equal to kt plus c1, and di dz is equal to k, so Iz is equal to negative kz plus c2. We know that the boundary conditions or initial conditions, lambda 0 equals 0, I 0 equals 0, thus the constants c1 and c2 equal 0. So what we see is that lambda t is equal to kt, I of z is equal to negative kz. All right, so B, we want to know, in the quasi-static approximation, well, E is equal to lambda over 2 pi epsilon s hat. Well, lambda is equal to kt. Go ahead and plug that in. B is equal to mu naught I over 2 pi s phi hat. So go ahead, plug that negative current in. And what we want to know is, do the Maxwell's equations get satisfied? So here, does the divergence of E equal 0? Okay. And yes is the answer because the s is canceled. Does the divergence of b equal 0? Yes, because there is no phi derivative, so that equals 0. All right. Does the curl equal negative curl of e equal negative b dt? 0 minus 0 equals 0? I think so. That'll work. Yes, and yes. Okay. And then does the curl of b equal the derivative of e with t? Got a lot of cancel signs. Okay, be careful with the curl. Again, with these directions, apply the appropriateness or appropriate component. Yes. And then we see epsilon's cancel. So, yep, we get mu naught k over 2 pi s in both. Yep, and you're good to go. Now for the Gaussian cylinder of radius s, Now, since we did the differential, now we have to do the integral form. So for a Gaussian cylinder radius S, about the z-axis at height z with radius dz, we have that E dot dA is equal to kt over 2 pi epsilon naught s times, well, the surface here would be 2 pi L, or 2 pi s times L, but L would be dz. So you see the 2 pi s's cancel, and that's equal to lambda dz over epsilon naught, which is equal to Q enclosed. So yep, that'll work. And then, well, clearly here B dot dA is equal to 0, since dA would be running downwards. Nothing really to worry about there. For a circular Amperian loop of radius S about the z-axis at height z, E dot dl is equal to 0. Again, they're running in different paths, so the field being orthogonal would lead it to 0 in both cases of E dot dl and B dot dA. And so what we need to show is that this is equal to negative d by dt of B dot dA, which again, it works out. 0 equals 0. Now, the line integral of B dot dl needs to equal to the current I, mu naught I, yes, we agree there. But that's equal to mu naught I equals mu naught epsilon naught dt by E dA, which we solved for earlier. Note that the integral B dot dA and integral E dot dA are 0 through this loop. All right, that's all we need to know, and we're good to go. That's wonderful. Good stuff.